In the diagram below, how much work is done by the electric field as a third charge, Q3, is moved from infinity to point B. So point B being right there. Okay, so whenever I see work, I see the word work and I see some word referring to motion, i.e. moved, I think of the equation work equals, whoa, crazy, work equals F dot dr. So we have a point from up here. We can choose any infinity and then bring it in. And since, yes we can. So we're going to choose this infinity up here just because it's convenient and bring it down to there. And so what this equation is saying, so this force here is going to be force due to electric field. So force due to electric field equals K Q1 Q2 over R squared. Where 1 and 2 doesn't mean this 1 and 2 here, it just means two different charges. So then what we're going to do, this is a dot product. So what it means is I can break down this vector here. Whoop. I know this is not going to be my best diagram. So we can break it down into this vector, I'm going to call it in the y direction. And we break down this vector, I'm going to call it in the x direction. Only the force that is parallel to the motion of the charge will create work. So moving since it's a conservative field, that's what electric fields are, means path independent. We can start up here and move all the way down here, or we can take this and move straight down and then to the right. And what this dot product means is this part with a y, because it's moving here. If we look at the forces here, so we have a positive charge here. That means it's going to repel, so it's going to create a force going that way. You have another charge here, it's going to attract, so it's going to create a force going that way. The net force will be this way. So when we're moving down like this, it's not going to matter. It's not going to contribute to the work. But when we take the charge from here and then move it towards B, that's the part that's going to count. So that's just what the dot product means. It's good to have a conceptual understanding of what that implies. All right, back to the equation. This is going to be a little bit of a derivation. I know this one is valuable, some of them aren't. I think this helps with understanding a little bit. Unless you have no experience with calculus, in case this is just daunting and cruel on my part. So Q1 over Q1 Q2 over R squared. Click, click, clack. Got it. Simplifying, since K and Q1 and Q2 will be constant for the motion. And then we'll do integral R to the -2. It's the same as 1 over R squared dr. Using the product rule, KQ1, Q2, we have R to the -1 over -1. This will be evaluated from, I'm going to say R initial to R final. And then, to get rid of this negative, we'll just kind of swap it around. KQ1, Q2 times, let's see if I can do this, 1 over R naught minus 1 over R final. And now, one of the things you normally see for the definition of voltage or potential energy, you usually see something like voltage equals KQ over R. Well, that's the voltage, and then potential energy will be KQ1, I'll put a little 1 there, Q1, Q2 over R. And what that really is it's the charge, whatever charge you have, times the voltage. And that's actually the same as over here, because voltage, you can't look at voltage in isolation. Voltage is always a difference between 2 points. Well, sometimes you'll see it as if it is just in terms of 1 point. What they mean by that is that this second point, let's see over here, this second point, either the R initial or the R final, usually the R initial, that will be infinity. So one of the definitions of voltage is taking a test charge from infinity. Infinity is not actually right here, it's further out. And then you bring it down to a given point. And that's a formal definition of voltage. So that's some kind of understanding about where the formula comes from. Okay, so looking at this then, and how we're going to apply this, we're now going to apply this formula, KQ1, Q2, 1 over R naught, 1 over R final, to both the electric fields generated by Q1 and Q2. So looking at it over, I'll do it down here. So I'm going to look at Q1 first. So this is work, or energy. Work due to, I'm going to call this 1, 3, due to charge 1 on 3, will equal K, move this down a little bit, Q1, Q2, times 1 over R initial, which will be infinity. 1 over infinity minus 1 over, and this is going to be 0.08, because the final radius is going to be 8 centimeters, which is 0.08 meters. Okay? Then we're going to add on to that work 2, 3, which is the work due to electric field of charge 2 on charge 3. KQ1, or Q2, Q3, 1 over infinity again, because we're starting at infinity, and we're going to go to 0.04, or 4 centimeters. Whoop. So do some simplifying real quick, and then we're going to add these two energies together. So this will be 0, because 1 over infinity is 0. I'm going to multiply top and bottom by 2. This gives 0.08. I'm going to be like, wow, why are you doing that? You'll see. And Q2 is same as Q1, just negative. So here, same as Q1, just negative. Okay. So when we simplify this, W1, 3 plus work 2, 3, total work, due to both particles, we'll say K, Q1, Q2, and let's see if we pull this out, this will be negative, that'll be positive. We'll do 2 over 0.08, yes, minus, I'm trying to keep all my minuses straight here, 1 over 0.08, which equals, and really I'm not too concerned about the sign because I'm going to check it at the end to kind of make sure I get the right concept going. Q12, 1 over 0.08. Okay, now I'm going to write this out in some sort of giant mathematical equation. K, that's a Coulomb's constant, so that's 8.99. I'm going to round that to 9, times 10 to the 9th, times Q1, I'm going to have to look at what that is again. I think it's 5.5 and 8.8, okay? So 5.5 times 10 to the negative 9th, nano, times 8.8 times 10 to the negative 9th, again nano, all over 8 times 10 to the negative 2nd meters, 0.08. Look real quick again, 8.8 nano, got it, good. Go team. Now we're doing some crazy cancellations. If I was more formal, I'd put units on, but I'm not. And they're time consuming and challenging. Not that things that are challenging shouldn't be done, but not right now. Okay, so here's some little bit of simplification. And then I'm going to write 10 to the 7th as 10 to the negative 1 times 10 to the negative 6. That way I get micro, because I think that's what they want the answer in. So we'll do 9 times 5.5 times 8.8 all over, and then this 10 to the negative 1 will be like 10 on the bottom over 80 times, and I'll do 10 to the negative 6 over here. So now, get the calculator, on, clear, 9 times 5.5 times 8.8 divided by 80, 5.445, about 5.445 microjoules. And it's going to be a little bit different because I use 9 instead of 8.99, but same idea, 5.445, right here, 5.445. Now I want to check real quick to make sure I'm correct on the sign. So the work done here, moving it down here, so the total net electric field due to Q1 and Q2 is going to be this direction. That'll be the force. I guess it's the electric field too. That's the force due to the electric field, and the motion, the net motion, that's going to be parallel to the force is this direction. So the F dot dr, same direction Therefore, this is going to be positive. Therefore, the work done is positive. Therefore, I'm going to go with 5.445. Not too hard of a question, and there's kind of ways to simplify this, but I think having an understanding of what I did here really would kind of help with when problems get a little bit more confusing. You're dealing with not just point charge, but various shapes. So I hope that helped. I will see you next time.